Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. 2 in the morning. Your phone is buzzing like a chainsaw. Pager duty. A Prometheus alert. Prometheus is a popular open-source monitoring tool that scrapes metrics from your servers. Says CPU is spiking on Web 03. You drag yourself out of bed, stare at 3 different dashboards, grep logs for 25 minutes before you even know if it's a rogue deployment or just noise. By the time you figure it out, the marketing site's been down for half an hour, and you're already fried. Now, what if I told you we can build an agent that does all of that? Detect, analyze, notify, while you sleep. In Part 8, we automated infrastructure code with Claude. Today, we're going fully agentic, a scheduled workflow that chains Prometheus, Claude, and Slack into an autonomous on-call partner, essentially your own site reliability engineer, SRE assistant. By the end of this lesson, you'll understand how to build an AI-assisted incident triage workflow on top of Prometheus. We'll start simple. Python retrieves monitoring data, Claude analyzes the evidence, and Slack receives a structured incident summary. Then we'll harden the design. You'll learn how to separate deterministic monitoring from AI analysis, protect sensitive telemetry, restrict the diagnostics AI can request, add human approval before critical escalation, and evaluate whether the AI is actually helping. The goal isn't to replace your SRE. It's to give your on-call engineer a better starting point when an alert fires. Before we build anything, let's clear up an important distinction. Traditional automation follows predefined logic. If CPU exceeds a threshold, send an alert. An AI-assisted workflow still follows a predefined path, but adds an LLM to interpret context. Fetch metrics. Analyze them with Claude. Create a readable summary. Send it to Slack. A true tool-using agent goes further. It can inspect the evidence, decide which approved diagnostic tool it needs next, examine the result, request another diagnostic if necessary, and stop when it has enough evidence to produce a useful conclusion. So our first version isn't going to be magically autonomous. We'll build AI-assisted automation first. Then we'll evolve it toward agentic behavior. Imagine your production API starts consuming more memory than usual. At the same time, HTTP 5xx errors begin increasing. Prometheus can tell us those measurements changed. But 2 metrics moving together doesn't automatically prove why the incident happened. That's where AI can help with triage. Claude can examine the evidence and produce something like, observed, memory utilization increased from 62 to 91%, while HTTP 5xx errors increased during the same period. Working hypothesis. The application may be experiencing memory pressure. Recommended next check. Inspect container restarts, recent deployments, and out-of-memory events. Notice what Claude did not say. Root cause confirmed. That's an important distinction. Metrics provide evidence. AI helps develop a hypothesis. Additional diagnostics help determine whether that hypothesis is correct. Here's the beginner-friendly architecture we'll build first. A scheduled job triggers our Python script. The script queries Prometheus for a small set of relevant metrics. Those measurements are converted into structured input and sent to Claude with clear SRE triage instructions. Claude returns a structured analysis containing observed evidence, a working hypothesis, confidence, recommended next checks. The script then posts that summary to Slack. For this lab, we'll use Cron because it's simple and makes every step easy to understand. But later I'll show you how this architecture changes for production, where we don't necessarily want to send routine healthy metrics to an LLM every 15 minutes. Once you understand the basic workflow, here's the architecture I'd move toward. Prometheus continues doing what it's excellent at, collecting metrics and evaluating deterministic alert rules. When an alert condition is met, Alert Manager triggers our triage service. Only then does the AI layer become involved. The triage service gathers relevant metrics and context, sends that evidence to Claude, and receives a structured analysis. If additional evidence is required, Claude can request one of our approved diagnostic tools. The final analysis goes to Slack for the on-call engineer. For critical actions, we can require human approval before escalation or remediation. So the production flow becomes Prometheus, Alert Rules, Alert Manager, AI-assisted triage, Approved Diagnostics, Slack, Human Decision. The AI enhances monitoring. It doesn't replace monitoring. You'll need 5 things before we start. Python 3.8 or newer on a Linux box. An Anthropic API key. Check the console for current pricing plans. The pay-as-you-go rates are cost-effective for testing. Access to a Prometheus endpoint that serves metrics. If you don't have one, you can spin up a local instance. A Slack incoming webhook URL from the Slack API site. That's where the alerts land. And cron access on that server to schedule the script. Once you have all 5, you're ready. Here's the first piece. Fetching metrics from Prometheus. The function sends a GET request to the Prometheus API with a PromQL query. For example, CPU idle time over the last 5 minutes. We wrap it in a try-except block, so a network hiccup doesn't silently kill the entire workflow. If Prometheus is down, we log the error and bail gracefully, critical for a headless job that runs at 2 a.m. Now let's build the analysis layer. And instead of just talking about prompt engineering, I'm going to show you the actual system prompt. Here's the foundation. You are an AI assistant supporting an on-call site reliability engineer with incident triage. Analyze only the evidence provided. Separate confirmed observations for hypotheses. Never claim a root cause unless the supplied evidence establishes it. If the evidence is insufficient, explicitly say so. Do not invent metrics, events, logs, deployment information, or system behavior. For every analysis, return severity, observed evidence, working hypothesis, confidence, low, medium, or high, recommended next diagnostic. Do not recommend destructive remediation unless the evidence clearly supports it. When additional evidence is required, request an approved diagnostic tool rather than guessing. Notice what we're doing. We're not asking Claude to find the problem. We're defining an operational contract. Evidence stays evidence. Hypotheses are labeled as hypotheses. Uncertainty is allowed. And when Claude doesn't know something, the correct behavior is to request more evidence, not manufacture an answer. I'll include this exact prompt with the starter project so you can modify it for your own environment. Finally, we deliver the intelligence. The Slack notify function takes Claude's summary and wraps it in Slack's BlockKit format, a header, a markdown section for the analysis, and a subtle footer noting it was auto-generated. This posts directly to your operations channel with proper formatting, not a raw blob of text. Set your webhook URL as an environment variable, and you're done. Quick checkpoint. What keeps Claude from jumping from CPU is high to the deployment caused the outage? It's the operational contract we built into the system prompt. Claude must separate observations from hypotheses. It must use only the evidence provided. It must admit when the evidence is insufficient. It must assign a confidence level. And when it needs more information, it should request an approved diagnostic instead of guessing. That's the key idea. A production AI prompt isn't just instructions for what the model should do. It also defines what the model is not allowed to assume. Before telemetry leaves your environment, treat it like production data. Prometheus labels can expose more than CPU and memory. They may contain internal host names, IP addresses, cluster names, application names, environment labels, tenant identifiers, URLs, or other information you don't want unnecessarily leaving your environment. So minimize the data before sending it. Remove labels Claude doesn't need. Mask or tokenize sensitive identifiers where appropriate. And never send secrets such as passwords, API keys, authentication tokens, private keys, or authorization headers to the model. Also verify your organization's AI policy and the current data handling terms of the AI service you're using. The safest principle is simple. Send the minimum amount of information required to perform the analysis. To set it and forget it, we'll drop a cron tab entry that kicks off this workflow every 15 minutes. The command uses the full path to Python in the script and pipes everything to a log file. So when you're debugging at 2 a.m., you can grep that log instead of guessing. Our workflow depends on multiple external systems, and any one of them can fail. Prometheus can time out. The Claude API can throttle a request. Slack can become unavailable. So each external dependency needs its own timeout, retry policy, logging, and fallback behavior. Let's look at Slack. Our Python logic can follow a simple pattern. First, try to send the incident summary to Slack. If the request fails, log the exception. Retry a limited number of times with backoff. If Slack is still unavailable, trigger an independent notification path. For this lab, that could be a simple SMTP email sent to the operations mailbox. The logic is essentially, try Slack. If Slack fails after retries, send email. If email also fails, write a critical error to the local log and expose a monitoring signal for the pipeline itself. The important word is independent. If Slack is broken, sending another Slack message isn't a fallback. In production, your secondary path could be PagerDuty, email, Teams, or another alerting system your organization already trusts. And don't forget to monitor the monitoring pipeline itself. Track successful runs. Failed Prometheus queries. Claude API failures. Slack delivery failures. Fallback activations, and the timestamp of the last successful execution. Because an automation that silently stopped running 3 days ago isn't monitoring anything, here's where the AI layer can earn its keep. On the left, raw metric values, labels, timestamps, query results. Useful to an engineer, but not necessarily useful at a glance during an incident. On the right, our Slack message organizes that evidence into 5 fields: severity, observed evidence, working hypothesis, confidence, recommended next check. For example, observed, CPU increased to 94% at arrow 213, HTTP 5XX errors increased during the same window. hypothesis, application workload, or a recent deployment may be contributing to resource saturation. Confidence, medium. Next check, compare deployment timestamps and inspect application error logs. That's much safer than root cause, bad deployment, roll it back. The AI's job is to accelerate investigation, not manufacture certainty. Okay, you built the workflow, it's running. Pat yourself on the back. But here's the thing nobody warns you about. What happens at 3 a.m. when Claude decides a routine spike is a disk failure and pages the whole team? A hallucinated critical alert is worse than manual. You've just injected noise into an already stressed on-call rotation. AI isn't always right, and blindly trusting its output is the fastest way to make your team hate automation. We're not done yet. Next few scenes, we're hardening this system so it doesn't wake people up for ghosts. Last checkpoint before the finale. First, what must you do to protect sensitive data before feeding metrics to Claude? And second, what's the worst thing that can happen if you blindly trust every AI-generated alert? Think about it. How much faster is this than manual triage? There's only one responsible answer. Measure it. For a simple incident, the automated workflow might gather metrics and produce a summary in seconds. A more complicated investigation involving multiple queries and diagnostics could take longer. So capture timestamps. When did the alert fire? When did AI triage begin? When was the summary available? When did the engineer acknowledge it? Then compare those measurements with your existing incident response process. The goal isn't to claim that AI is always faster. The goal is to determine whether it reduces the time engineers spend gathering basic evidence before they can start making decisions. Now let's make the cost calculation concrete. Your cost depends on 4 things: how often the workflow runs, how many input tokens you send, how many output tokens Claude generates, and the current price of the model you're using. Let's use a simple example. Suppose your system performs 100 AI-assisted checks per day. Each investigation sends an average of 500 input tokens and generates 200 output tokens. Over 30 days, that's 3,000 investigations. About 1.5 million input tokens and about 600,000 output tokens. Now take those token totals and multiply them by the current input and output prices for the Claude model you've selected. For example, if your model hypothetically cost $1 per million input tokens and $5 per million output tokens, the calculation would be 1.5 million input tokens times $1 equals $1.50. 600,000 output tokens times $5 equals $3. Estimated monthly AI cost, $4.50. Those prices are only an example. Model pricing changes, so always check the current Anthropic pricing before estimating your real production cost. And remember, you probably don't need 100 AI investigations every day. If Prometheus and Alert Manager handle normal monitoring and invoke AI only when a meaningful alert occurs, you can reduce unnecessary token usage, noise, and cost. That's another reason the event-driven production architecture is stronger than blindly sending healthy metrics to Claude every 15 minutes. At this point, we've built something useful. Prometheus provides the evidence. Claude analyzes it. Slack delivers the result. But there's a limitation. Claude can only reason about the information we give it. Imagine the metrics show memory climbing rapidly and HTTP 5xx errors increasing. Claude might reasonably say, memory pressure may be contributing to the failures. But what should it check next? An experienced SRE might inspect container restarts, application logs, deployment history, or service health. That's where we can evolve from a fixed AI-assisted workflow into controlled agentic triage. Instead of giving Claude unrestricted access to our infrastructure, we'll give it a small collection of approved, read-only diagnostic tools. Claude can choose which tool it needs, inspect the result, update its hypothesis, and request another diagnostic if necessary. But before we give AI more capabilities, we're going to keep one important guardrail. Critical escalation still requires human approval. The more autonomy we add, the more important controlled permissions, observability, and human oversight become. Pause for a moment. A fully headless AI incident response sounds amazing, but what can go wrong? And what key quality should your alert message have to be instantly actionable? Our first workflow was linear. Fetch metrics, analyze, notify. Now let's evolve it. A tool using Agent can look at the initial evidence and decide which approved diagnostic it needs next. For example, Prometheus reports high memory usage. Claude requests recent container restart information. The tool returns the result. Claude observes repeated out-of-memory restarts. It then requests recent deployment metadata. The system returns a deployment timestamp matching the beginning of the incident. Now Claude has stronger evidence for its hypothesis. This creates a loop. Observe. Choose an approved tool. Inspect the result. Update the hypothesis. Repeat only when necessary. Then summarize. That's much closer to agentic behavior than simply inserting an LLM into a fixed automation pipeline. This is one of the most important security rules in the entire project. Do not give the model an unrestricted terminal and let it invent SSH commands. Instead, expose a small set of approved diagnostic functions. For example, get disk usage, get memory stats, get service status, get recent errors, get deployment history. Claude can choose which diagnostic it needs, but your application controls what each function is allowed to do. Validate the host, validate the arguments, set strict timeouts. Use read-only permissions whenever possible. Log every tool request, and return only the information needed for analysis. The model gets tools. It does not get your shell. That's the difference between controlled automation and giving an AI unrestricted access to production infrastructure. Let's separate what we've actually built from where this architecture can go. Our core workflow uses Prometheus for monitoring data, Python for orchestration, Claude for analysis, Slack for notification. From there, you can extend the architecture. Alert Manager can trigger triage only when an alert condition exists. Jira can create an incident ticket. PagerDuty can handle escalation. Deployment APIs can provide release history. Logging platforms can provide relevant application errors. But don't connect everything on day one. Start with a small read-only workflow. Measure its quality. Then add capabilities one at a time. Every new tool increases both what the agent can accomplish and what can go wrong. Let's look at the final Slack alert. At the top, severity and affected service. Then, observed evidence. For example, CPU reached 94% and 5x errors increased immediately after a deployment. Next, work in hypothesis. The recent deployment may be contributing to resource saturation. Then, confidence, medium. And finally, recommended next checks. Compare application metrics before and after the deployment. Inspect error logs. Check container restart events. Notice what the alert doesn't automatically say. Roll back now. The AI gives the on-call engineer organized evidence and a sensible next investigation step. The human still makes the operational decision. Before this system ever wakes someone up at 2 in the morning, test it. Build a small evaluation set using incidents where you already know what happened. Include different scenarios: CPU saturation, a memory leak, disk exhaustion, a failed deployment, database latency, a network problem, and at least one normal traffic spike that should not become an incident. Then measure the AI. Did it interpret the evidence correctly? Was its hypothesis supported by the data? How often did it create false positives? What did it miss? Were its recommended diagnostics safe and useful? How long did triage take? And what did each investigation cost? Don't evaluate an AI monitoring system by asking, "Did the Slack message look impressive?" Evaluate it by asking, "Did it consistently help engineers investigate incidents without creating dangerous noise?" Once your evaluation looks promising, don't immediately connect the system to production paging. Run it in shadow mode. Let your existing monitoring and on-call process continue exactly as it does today. At the same time, let the AI analyze the same incidents quietly. Don't let it page anyone. Don't let it remediate anything. Compare its analysis against what your engineers actually discovered. Track false positives. Track missed incidents. Track incorrect hypotheses. Track whether its recommended next steps would have helped. After you've collected enough evidence, you can decide whether to expand its role. Production trust should be earned with measurements, not assumed because the demo worked once. You started with a simple workflow: Prometheus, Python, Claude, Slack. Then you made it safer. You separated deterministic monitoring from AI analysis. You changed root cause into evidence, hypothesis, confidence, and next diagnostic. You protected sensitive telemetry. You added resilient failure handling. You gave Claude allow-listed diagnostic tools instead of unrestricted shell access. You kept humans involved in critical decisions. And finally, you evaluated the system and ran it in shadow mode before trusting it with production escalation. That's the real lesson. Building an AI monitoring demo is easy. Engineering one that your operations team can actually trust is the valuable skill. If this changed how you think about on-call, subscribe and hit the bell. I want to hear what's the first automation you'd build. Drop it in the comments. And before the next video on compliance audits, grab Logstash's free Grok debugger to get a head start, parsing logs automatically. Link in the description. No fluff, just more actionable AI for IT pros. Next up in the Claude Masterclass, we'll tackle security compliance audits and log analysis, the stuff that turns a good admin into a great one. See you there. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.